This is our AP Review Topic 6, the miscellaneous questions, and this is the remaining questions that I did not cover when I was doing the introductory to this topic. Okay, so I'd like to begin with the problem from 2018. Definitely after this test, my students came back talking about the Plankton problem and how, Miss Murray, there's this infinite column of water, and we were supposed to find how many plankton there were in an infinite column. And it was funny to hear them talking about it. But anyway, all right, let's take a look at this. It says that researchers on a boat are investigating plankton cells in a sea. At a depth of h meters, the density of plankton cells in millions of cells per cubic meter, so this is the density, is modeled by this equation. So P is the density for h is 0 to 30, and h was again the depth of the water, and is modeled by F for h greater than or equal to 30. So the density is modeled by two different functions, P and F. Okay, P is good for 0 to 30, F is good greater than that. And I should mention that this was number 2 on the test, so this is with a calculator. Okay, and it says that F is not explicitly given. All right. So first of all, they ask us to find P prime at 25, and then using correct units, interpret the meaning of P prime at 25. So P prime at 25 is going to be a very straightforward calculator process here. So I'm going to go ahead and put P in for my Y1, because I'm assuming I'm going to have to use it over and over again in this problem. So 0.28. I'm going to let x be h, so x squared e to the negative 0.0025 x squared. I'm taking a look at that, making sure it's correct. It looks good for me. And I know that this is only good for 0 to 30 for h. All right. Now to my home screen, I want P prime at 25. So I'm going to write what I'm doing. Got to tell AP what I'm doing. I'm finding P prime at 25. So math 8 with respect to x, because that's my variable, of y1 at 25. So this is it comes out to be negative 1.179, and that is the rate of change. It's the rate that the density is changing at 25 meters. So because P is density, so P prime would be the rate density is changing at a depth of 25 meters, right? So that's what I'm going to say. This means the density of cells is changing at a rate of negative 1.179. I need to give units for that now. Okay, P's units are millions of cells per cubic meter. H is in meters. So this number will be in millions of cells per cubic meter per meter. The per meter is the H part, right? So it's always units of P divided by units of H in this case, right? At a depth of 25 meters. Let me see if that makes sense. The density of cells is changing at a rate of negative 1.179 millions of cells per cubic meter per meter at a depth of 25 meters. That's fine. I could have said the density of cells is decreasing at a rate of, and if you say decreasing here, then do not put the negative. Just put decreasing at 1.179. If you say decreasing at a negative, you're undoing that negative, so make sure you get that right. All right, so that looks good. Part B. Consider a vertical column of water in the sea with horizontal cross-sections of constant area 3 square meters. Okay, so there's a vertical column of water in the sea. I don't know that it's a cylinder, but I'm going to kind of pretend it is just for ease of my mind. Okay, and each cross-section of this, each cross-section has area 3 square meters. So each cross-section, wherever it is, that area is 3 square meters. That area is. Okay? So this, remember, this is depth of water. So we're starting the depth at 0, and then we're going down to, we're going to be going down to 30 meters. Okay? So to the nearest million, how many plankton cells are in this column of water? I know that at a depth, the density is P of H, right? The density is P of H at any depth, H. So I need to add up all of those from 0 to 30, and that will give me the number of plankton cells in that column of water. So when we add up, we're going to use an integral from 0 to 30, and I need P of H times the area, right? So 3P of H dH. If you're wondering, if when you're taking one of these problems and you're not sure about the setup of this, keep in mind we're getting the millions of plankton cells. So we're getting how many cells, right? So our units for this 3, those units are in meters squared, right? That was our area. Our units for P are cubic our units for P are millions of cells per cubic meter. So millions of cells per cubic meter, right? And dH, even though it's very thin, it still has units, and that's in meters because H is in meters. Look at how the units cancel out. We have meters cubed on top, meters cubed on the bottom, those canceled out, and we're left with cells, right? So even just doing a little unit analysis here confirms that this is the correct setup for this. So we'll go to our calculator. Math 9, 0 to 30, 3y1, and I get I'm going to write down 1675.415. They want me to, they said in here though, to the nearest million, and this number is in millions, so this is approximately equal to 1675 million plankton cells. Okay, so these two problems just now were worth, each was worth 2 points. This first one was worth 1 point for the answer, 1 point for that answer, and then 1 point for the meaning of that answer with units. So that was worth 2 points. This problem here was worth 2 points as well. 1 point for the integral, 1 point for the answer. Okay? All right. And by the way, the global average on this problem was 3.5. So when you did this problem, ask yourself how many points you got. Were you greater than or less than the global average? Okay, let's take a look at part C. There is a function u such that f is less than u. F, which is positive, is less than u for all h greater than 30. Okay, so here we are h greater than 30, right? Which is where f applied. And it says this integral, and the integral from 30 to infinity of u of h is equal to 105. Okay, the column of water in part B is k meters deep now. So it was 30 meters deep and now it's k meters deep where k is greater than 30. Write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column. Well, this won't be bad because all we have the number of plankton cells from 0 to 30 meters deep, and now we just needed to go an extra some more, right? So here we have another column of water, or you can think of it as the same column of water. It's just deeper, okay? And from 0 to 30, we know how many plankton cells are there. We found it up here in part B. And now we need to go from 30 to k and do the same thing. So I'm going to write an expression involving one or more integrals that gives those plankton cells. It's going to be 0 to 30 of 3p of h. That's what we had above. And then we're going to add the integral from 30 to k of the same, of 3f of h, 3f of h. Because now we're using f because p was only valid from 0 to 30. Okay? So did I do that fine? Did I have, yeah, I think that's good. So that was the expression, right? And that was worth another 1 point, by the way. Okay, just the expression. And now it says, explain why the number of plankton cells in the column is less than or equal to 2,000 million. So I'm assuming I need to bring u into the picture here, right? So K is the depth of the water, right? K is the depth of the water. So K is going to be less than or equal to infinity. It's bounded. It's a number, right? And I know that F is less than U. F is less than U, and the infinite integral for U from 30 to infinity is 105. So I'm going to say that I'm going to make a couple of statements here. I'm going to say that F, I'm just rewriting what they have up here, F is less than or equal to U, right? F is less than or equal to U. So the integral from 30 to k of 3f of h dh is less than or equal to the integral from 30 to k of 3u of h dh, right? Has to be true. Okay? And now, since k is less than infinity, I can say that, I'm going to say that k is less than infinity. So the integral from 30 to k of 3u of h dh is less than or equal to the integral from 30 to infinity of 3u of h. Does that make sense? And I can bring the 3 out. So I can say equals 3 times the integral 30 to infinity of just u of h dh. And then that is 3 times 105 from the information they gave us up there. So coming back over here, this value is 165. So this this value then is less than or equal to 1675 plus 3 times 105. And that is equal to, I guess I'll grab my calculator real quick here to see what that's equal to. 1675 plus 3 times 105. 1990, which is less than or equal to, or it's just less than 2,000. So we mathematically explain why the number of plankton cells has to be less than or equal to 2,000 million. Okay, so this was a challenging one. I can see why my students came back talking about it. This was worth 3 points. 1 point was for the integral expression. So that was this piece right here. 1 point was for compares improper integral. Compares improper integral. I guess that's right there. My comparison with the improper integral. And then 1 point for explanation. So 3 points total for that. Okay? Alright, one last little part of this problem. A boat is now moving on the surface of the sea. At time t is greater than or equal to 0, the position of the boat is x of t, y of t, where x prime is this function and y prime is that function. Find the total distance traveled by the boat from time 0 to 1. Well, this was probably a very nice relief for my students because they knew this formula. We spent a bit of time going back over parametric equations and the formula for total distance traveled. So total distance, this is just a straightforward formula problem. Total distance from 0 to 1 is the integral 0 to 1 square root x prime squared plus y prime squared. And I know when you guys are getting this topic, we haven't yet done our parametric review, but this, when we get there, you'll remember that and it would not be a problem for you. Okay, and this is just stick it in your calculator and go. So let's do that. So math 9, 0 to 1, square root. Okay, I need to square 662 sine of 5t. Carefully square that, right? Plus 880 cosine 6t. So carefully do that. See if I punched it in right here. It's going. Okay, so I got 757, and it looks like we can round it. So 757.456, and that would be in meters. Okay. They didn't tell me to use units, so I don't need to write units there. Okay, this part was worth 2 points. 1 point for the integral, 1 point for the total distance. Okay, so if this problem didn't freak out my kids too badly, I'm sure they got these 2 points. Okay, and I'm pretty sure they would get these 2 points. So already that's 4 points, and that's above the global average. I'm hoping that they can pull some points from B and C as well and get above that global average. Okay, so that was the problem from 2018. Okay, now let's take a look at the problem from 2015. This was number 5, no calculator. Consider this function, they say, where k is a non-zero constant. The derivative of f is given by this, so that was nice of them. They gave us the derivative of f. The reason AP likes these is that they can do so much with these, especially when they put a k in or something where they can say, let k be this, now let k be that. They like these, okay? In part A, let k be 3. So that makes f equal to this. It says write an equation for the line tangent to the graph of f at the point whose x-coordinate is 4. So line tangent, we should all know how to do that, right? We need a point and we need a slope. So first of all, the point will be f of 4, right? F of 4 is 1/4. Okay? And now we need the slope. The slope at 4. The slope at 4. So I'm putting 4 in for x in the slope. K is 3, right? K is 3. So K is 3. 3 minus, so I'll have 3 minus 2 times 4 over 16 minus 3 times 4 squared, right? This is, and you could leave it just like that, and that's fine, and go write your equation of the tangent line, and that would certainly be fine to do, okay? This is 3 minus 8, negative 5. 16 minus 12 is 4, and 4 squared is 16. So negative 5 over 16 will be the slope, and so the equation of the tangent line will be y minus the y value is equal to the slope times x minus the x value. And that's that. This was awarded 1 point for the correct slope, and then 1 point for the tangent line equation. 2 points. Okay. Part B. Now we're going to let k equal 4. So now this is f of x. Determine whether f has a relative min, relative max, or neither. So we have a choice. We can use either the first derivative test or the second derivative test. We'll see which one is easier for us. So for either one, we need to begin with f prime, right? So f prime, I'm going to take the f prime they give us, and I'm going to go ahead and put 4 in for k. So f prime is 4 minus 2x over x squared minus 4x squared. Okay? So I'm trying to determine whether f has a relative min, max, or neither at x equals 2. So let's find f prime at 2. F prime at 2. On the top we're going to have 0, right? That'll be 0 over. On the bottom I have 4 minus 8. 4 minus 8 squared, right? So that'll be a negative 4 squared is 16. So f prime of 2 is 0. That means that we could have a min or a max, but we still might be neither. It depends on what's happening around there. Okay. I think I might just do a first derivative test here, and let's check 2. We found that f prime has its slope is 0 here, so let's check on either side of this. And like if we put in like 1 for x, we'll have 4 minus 2, so we have positive on top, and we definitely have positive on the bottom, so this will be positive on this side. And on the other side, if we put 3 in, we'll have the top is greater than 0, so this will be a negative over here. So f prime went from positive to negative, therefore we have a relative max, right? So I'm going to say f has a relative maximum at x equals 2 since f prime goes from positive to negative there. We could have used the second derivative test, but that would have required me to take the derivative of this, and it's definitely doable, not too bad really, but and then you would plug in 2 and see if you get a positive, negative, or 0 there. It would have been fine to do it that way as well. This was worth 2 points. 1 point for considers f prime of 2, and then 1 point for your answer with justification. 2 points total. Okay, let's take a look at part C. We're going to find the value for k for which f has a critical point when x is negative 5. Find the value of k. Well, a critical point, and I'll say that, is when f prime equals 0 or f prime is undefined. Okay? So I'm going to take f prime that they give me, and first of all I'm going to consider, is there a value of k that makes the denominator 0, right? Is there a value of k that makes the denominator 0? And there is a value of k that makes this denominator 0. That would make f prime undefined. However, that value of k that makes f prime undefined would also make f undefined. And you cannot have a critical point when the original function is undefined there. So I don't need to worry about the value of k that makes f prime undefined here. All I need to do is find out what value of k makes f prime have f prime be 0 when x is negative 5, right? When x is negative 5. So I'm going to multiply both sides by that denominator, right? And k will be 2x. So f has a critical point at x equals negative 5 when k equals negative 10. Okay? And this was just worth 1 point for the answer. Part D. Let k equal 6. So now this is our f. Okay, first of all, find the partial fraction decomposition of f, and then find the integral of it, the antiderivative. So it's nice that they said find the partial fraction decomposition, because that's what you would have to do to find this antiderivative. So that was kind of nice of them. So let's take this and break it apart. Partial fractions. This, by the way, factors into x times x minus 6, right? So there's the breakdown of that. If we multiply both sides by x squared minus 6x, we get 1 is equal to a times x minus 6 plus b times x. We can let x be anything we like. I'm going to begin by letting x be 0. If I let x be 0, this term zeroes out, and I have 1 is equal to negative 6a, which means a is negative 1/6. If I let x be 6, 6, then I have 1 is equal to 0 plus 6b, which means b is positive 1/6. And so I can say that f of x is equal to negative 1/6 over x plus 1/6 over x minus 6. And that's the partial fraction decomposition. And now I can come and find the integral of f of x using that partial fraction decomposition. And now it's a very simple little integral for us. Negative 1/6 natural log absolute value x, and the derivative here is 1, so plus 1/6 natural log absolute value x minus 6 plus c. This was worth 4 points. 2 points for the partial fraction decomposition, and 2 points for the general antiderivative. Okay, next up we're taking a look at the BC problem from 2008, number 5, no calculator. It says the derivative of a function f is given by this equation for x is greater than 0, and they tell us that f of 1 is 7. So we'll have to keep that in mind. Not sure why they're telling us that. Okay. The function f has a critical point at x equals 3. So we know what a critical point is. It's when f prime is either 0 or undefined. At this point, does f have a relative min, max, or neither? So again, I can think of 2 ways to do this, either the first derivative test or the second derivative test. The first derivative test just tests a number line for f prime. The second derivative test, you find the second derivative, of course, and then you find, since f has a critical point at x equals 3, you're looking at f double prime at x equals 3, and you're asking yourself, is that positive, negative, or 0? Okay? So either one is fine. The second derivative will be really easy to find here, so I think I'm just going to do that. Okay? So f prime at 3 is indeed 0. So that's the first step in the second derivative test. And now the second derivative of x, I'm doing the product rule. So the derivative of x minus 3 is 1 times e to the x plus, now leave your x minus 3 alone, the derivative of e to the x is e to the x. Okay? This is equal to, I'm going to factor out an e to the x, and I'll be left with 1 plus x minus 3, right? Which is x minus 2. And now f double prime at 3, that's what we want to find out. What is f double prime at 3? F double prime at 3 is e cubed times 1. That's positive. That's positive. It's greater than 0, right? So these two things together say that f has a relative min, right? Minimum, because if f double prime is positive and there's a 0 slope, you're looking at a positive, concave up, and a 0 slope. It has to be a relative minimum at x equals 3. Since f prime of 3 is 0 and f double prime at 3 is positive. So that was using the second derivative test. Again, we could have done this by the first derivative test as well, and that would have worked out fine. In fact, let me show you how that would have worked out if you did the first derivative test. We've got f prime of 3 is 0, because when you put 3 in for x, you get 0. And then you would do a number line test, testing 3, and by the way, this is f prime. 3 would be the only critical point, right? Because the x is always positive, and the only thing that could make f prime 0 is this part, and the only thing that makes that 0 is 3. So it's the only thing, and we know we're greater than 0 here anyway, but regardless, f prime would go from, okay, so if I test like 1 here, I'll get a negative times a positive, so negative. If I test anything bigger than 3, I get a positive. So again, this means f is decreasing and then increasing. So that is, I can say f has a relative min. I would write that out. F has a relative min at x equals 3, since f prime goes from negative to positive there. Okay, so either one, first derivative test or second derivative test, work well. This was worth 2 points. 1 point for saying it has a minimum at x equals 3, and 1 point for your justification, whichever one you chose. But it needs to be one of them. Okay? All right. Part B. On what intervals, if any, is the graph of f both decreasing and concave up? F decreasing, F concave up. So f is decreasing when f prime is negative. F is concave up when f double prime is positive. So we're looking for what intervals is f decreasing, is f prime negative and f double prime positive on. So f prime, which is this, is 0 when x is 3. We know that from above. F double prime, if you hadn't used the second derivative test in part A, you would need to find the second derivative like we did here. But since we already did it, I'm going to say that this is equal to e to the x times x minus 2. And that is equal to 0 when x is 2, right? So if I do a number line, I'll put 0 here because we're only looking at x is greater than 0, 2, 3, and then we'll go on. I'm going to put f prime on the bottom, f double prime on the top here. So from 0 to f prime will only change around 3, and we know that anything below 3 makes f prime negative. Anything over 3 makes f prime positive. For f double prime, anything below 2 will make f double prime negative. Anything above 2 will make f double prime positive. So we want to know where f is decreasing and concave up. F is decreasing from 0 to 3. F is concave up from 2 to 3 in that interval. It's actually concave up all the way from 2 to infinity, but for where it's both decreasing and concave up, 2 to 3. So f is both decreasing and concave up on 2, 3, or you can say 2 is less than x is less than 3. If you'd rather do it in inequality notation, that's fine. Since f prime is less than 0 and f double prime is greater than 0, there. That was worth 3 points. 2 points for finding f double prime, and 1 point for the answer with reason. And then they just say, find the value of f of 3. The value of f of 3. We know f prime. We know an initial condition, so we can find any other point, right? Using the first fundamental theorem of calculus. I'm going to set up first fundamental theorem. F of 3 minus f of 1, since that's our known, is equal to the integral from 1 to 3 of f prime. Okay. F of 1, they tell us, is 7. F prime is x minus 3 e to the x dx. Okay. So clearly they're asking the meat of this is finding this antiderivative. So looking at this, I cannot do a u sub. I would let u be the exponent on the e, but that's not going to work for me because we have this extra x out here, right? So it's not a u sub problem. This is a by parts problem. Algebraic times a transcendental where you cannot do u sub. Always make sure you test u sub first though, okay? So I'm going to go off to the side, do by parts. Since we have algebraic and e to the x, I'm going to use the tabular method, the table method. Remember, we'll put u and dv. Under u, I'm going to put x minus 3. Under dv, I put everything else. We differentiate u until we get to 0, right? Take the derivative until you get to 0. Integrate the dv. We integrate dv. So e to the x, the integral of e to the x is e to the x, and then keep on going until you're lined up with the 0, right? Integral e to the x is e to the x again. This seems awfully easy. I'm wondering, it makes me look and see if I'm doing something wrong. We multiply diagonally, and don't forget positive, negative, positive, negative, positive, negative, all the way down, right? So this will be f of 3 will be, I'm bringing the 7 over, plus e to the x times x minus 3 minus e to the x from 1 to 3. So f of 3 is 7 plus, put 3 in for x. When you put 3 in for x, this is now 0, minus e cubed, minus, and now we put 1 in for x. When we put 1 in for x, we get e times negative 2 minus e to the first. And that would be a safe stop spot right there. Okay? And that's that problem. This was worth 4 points. Let's see how they did it. 1 point for uses initial condition. 2 points for your integration by parts. And then 1 point for your answer. So, did not think that was too bad of a problem. Okay, now we're moving on to the problem from 2007. This was from AB, but I thought it was a good problem. That's why I included it here too, okay? It's good review of some concepts. All right, it says that the function f and g are differentiable for all real numbers. Okay, g is strictly increasing. We'll probably need that, right? That's an interesting piece of information. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by this. Okay. Here's function h. First of all, explain why there must be a value r for in between 1 and 3 such that h of r is negative 5. Okay. So, first of all, it's a value of r. Explain why there must be a value of r. That's intermediate value theorem, you guys. Okay? So, for intermediate value theorem, I first need to state that h is continuous, right? What about this problem tells us that h is continuous? Well, h is a composition of two differentiable functions. Therefore, h is also differentiable. If it's a composition of differentiable functions, then it is also differentiable. Okay? And if it's differentiable, it must be continuous. So that's what I need to state. H is a composition of f and g, which are given to be differentiable. Therefore, h is also differentiable. And therefore continuous. And of course you can word that differently, but get your point across. State why in an intelligent way, state why h has to be continuous. All right, now comes kind of the meat of this part of your problem. I want to show that -5 is between h of 1 and h of 3. So I need to find h of 1 and h of 3. And hopefully -5 will be between there. So h of 1 is f of g of 1 minus 6, right? G of 1 from the table, G of 1 is 2. F of 2 is 9. So h of 1 is 3. Now we're going to find h of 3. That's f of g of 3 minus 6. G of 3 is 4. F of 4 is -1. So h of 3 is -7. And -5 is between h of 1 and h of 3. You can write that as an inequality. You can say h of 3 is less than -5, which is less than h of 1. You can say that as well. Or you could write it verbally like I just did. Therefore, by IVT, and you don't have to say by IVT, you can just say therefore, there must exist a value R for R is between 1 and 3, such that h of R is -5. They could have said -4, -3, -2, -1, 0. They could have said 1.5. They could have said lots and lots of numbers. They just picked -5. Okay? That was worth 2 points. 1 point for h of 1 and h of 3, and 1 point for your conclusion using IVT. Part B. Explain why there must be a value of c between 1 and 3 such that h prime of c is -5. Okay. This is MVT because they give us h. They're talking about why there must be something regarding h prime. I know that's MVT. So I first need to say that h is continuous on the closed interval and differentiable on the open interval. That's what we need for MVT. Well, I've already said above that h is differentiable and continuous. I said that in part A, so I really don't need to rewrite that whole thing here, okay? I think I will just say, as stated above, as stated in part A, h is continuous and differentiable. So I don't have to rewrite the whole thing there saying why it is, because I already set it up there. Okay? Now I want to show that between 1 and 3, the average slope is -5. The average slope. So I need h of 3 and, I need h of 3 and h of 1 again. So h of 3 minus h of 1 over 3 minus 1, that's our average slope, right? Is equal to, I found both of those up in part A, right? Is equal to -7 minus 3 over 2. That's -10 over 2, which is -5. I'm breathing a sigh of relief that we got -5, because now it's just a matter of writing our statement by MVT, which again, you don't have to say by MVT, you can just say therefore. But by MVT, there exists, and now I just come up and read this, a value C for C between 1 and 3 such that h prime of C is -5. Not too bad. So the way this was scored, 1.4 h of 3 minus h of 1 over 3 minus 1, and then 1.4 your conclusion. Pretend I spelled that right, using MVT. Okay. Next up, let W be the function given by this integral. Find the value of W prime at 3. Okay, well first we need to find W prime of x. To find W prime of x, we're taking the derivative of both sides, right? With respect to x, because that's our variable here. The derivative of the integral, we're using the fundamental theorem, the second part of the fundamental theorem of calculus. So that is, you replace the t here with g of x, and then you multiply that by the derivative of g of x. So that's going to be f of g of x times g prime of x. And when you go to put in the 1, it would be f of 1, but then you're multiplying by the derivative of 1, which is 0. So that part of it is 0. Doesn't matter what constant is here. If it's a constant, that part of it is going to be 0. So that is W prime of x. Now we're going to find W prime of 3. So we put 3 in for x. Okay, g of 3 from the table. G of 3 is 4. G prime of 3 is 2. F of 4 is -1. So f prime of 3 is a -2. This was also worth 2 points. 1 point for applying the chain rule. That's our G, remembering to do the G prime. And then 1 point for the answer. Okay, part D. Part D is kind of why I gave this problem to you. Well, the whole thing is good though. The whole thing is good, but we haven't talked about inverse functions for a while. So they give us that G inverse is the inverse function of G. Write an equation for the line tangent to the graph of y equals G inverse at x equals 2. So I know for the equation of a line, I need a point and a slope, right? I need a point and a slope. So for the point, I need the point to be on G inverse, right? Need the point to be on G inverse. And I know that the x coordinate is 2. I know that from right here. I don't know what the y coordinate is. Now let's think about what inverse functions are. If G inverse has an x coordinate of 2, that means on G, the y coordinate is 2, right? That's how inverse functions work. And G inverse's y coordinate will be G's x coordinate. So I need to go, I have the table up there, I need to go to the table and find out what x value makes G 2. What x value makes G 2. So here's G. The x value that makes G 2 is 1. So that tells me that its x coordinate is 1, therefore on G inverse, the y coordinate will be 1. Okay? The slope of G inverse at x equals 2, okay, is, all right, now we need its G inverse's slope at its x value. Well, we need to know that the slope of G inverse is the reciprocal of the slope of G at its point, right? So slope of G at x equals 2 is, the slope of G at x equals 2 is 1. Is 1. The slope of, oh, I'm sorry, not at x equals 2, at x equals 1, because on G, we're not looking at when x is 2, we're looking at when x is 1, right? So when x is 1, the slope of G is 5. So on G inverse, the slope at its coordinating point is 1 over 5, the reciprocal. So the equation of the tangent line will be y minus the y value is the slope times x minus the x value. This was worth 3 points. 1 point for G inverse at 2, just the point. 1 point for the derivative of G inverse at 2, the 1/5, and then 1 point for the tangent line equation. So I'm interested to see if you guys could figure that out. It's been a long time since we did that. So I'm wondering how far you got down that road. Okay, let's move on to this last problem. This is the problem from 2019, and the global average for this problem was 4 points. Okay, here's number 5, no calculator. Consider the family of functions this. So this is another one of these. Here's f of x, and there's a k involved. They can let k be anything and give us lots to do with it. For part A, find the value of k for k greater than 0, such that the slope of the line tangent to f at x equals 0 equals 6. The slope of the line tangent is equal to 6. That means f prime is equal to 6, right? It's not f prime of 6, it's f prime is equal to 6 when x is 0. So that's telling us f prime at 0 is equal to 6. Okay? So that's my thought process when I look at this. So I want f prime, so I need to take the derivative of this function. So here's my f of x. And we're going to find the derivative. Either the quotient rule, or you can pull this to the top and use the chain rule. Either one. Okay, I'm just going to use the quotient rule. If you use the quotient rule, you're starting up on the top with that 1, and you're taking the derivative of 1, and the derivative of 1 is 0. Okay, so be careful with that. The derivative of the top is 0. So then that whole first term is going to be 0. And then we'll have a minus for the quotient rule. There's a minus there as part of the quotient rule. And then we need the derivative of the bottom times the top, right? Well, the top is just 1, so this will just be the derivative of the bottom. So 2x minus 2, all divided by the bottom squared. Okay? If you did, by the way, FYI, if you did pull this to the top, then your equation would be that. And if you took the derivative here, you get negative x squared minus 2x plus k to the negative 2, because you subtract 1 from your exponent, and then you multiply by the derivative of the inside. And do you see that that is identical to what we have here? It's the same thing. The reason I kind of like the quotient rule is because we don't have to move this to the bottom. You get it immediately. Okay. So now that we're saying, now they want, we know when x is 0, this is 6, and they want us to find that k. So I'm going to put 0 in for x, and set that equal to 6, and solve it for k. So we have 2 over k squared is equal to 6. That means k squared is 2 over 6. So k is plus or minus 1/3, 1 over the square root of 3, k is plus or minus 1 over the square root of 3, but since they told us that k is greater than 0, k must only be 1 over square root of 3. This was worth 3 points. 1 point for the denominator of f prime of x. So 1 point just for that denominator. 1 point for the entire f prime of x, and then 1 point for the answer. So how did you do on that one? Part B. For k equals -8, find the value of this integral. Okay, we can do that. Let's see. We have the integral from 0 to 1, and I'm putting -8 in for k, right? So 1 over x squared minus 2x minus 8. And my question is, how do we take that derivative? How do we find the antiderivative? Okay? It's not a u sub because we can't let u be the bottom. Please, please, please do not tell me that this is a natural log of the bottom, okay? Because the derivative still has an x in it. So you cannot do a u sub here, okay? We can factor that denominator though, can't we? We can factor that. And when you factor it, you get x minus 4, x plus 2, right? Yes. So this is a partial fraction one. This is a partial fraction decomposition. So once we break it down, this will be very easy to find the antiderivative of. So I'm going to multiply both sides by x minus 4x plus 2, and we get 1 is equal to a times x plus 2 plus b times x minus 4. We can let x be anything we like. I'm going to begin by letting x be a -2. So this will be 1 is equal to, that's 0. This is -6b. So b is -1/6. Next I'm going to let x be 4. Now this part zeroes out and I get 6a. So a is positive 1/6. So my integral becomes the integral 0 to 1 of 1/6 over x minus 4 plus -1/6 over x plus 2. Now these two antiderivatives are natural logs. So 1/6 natural log, absolute value x minus 4, minus 1/6 natural log absolute value x plus 2 from 0 to 1. I had to write smaller because I didn't move this, so I should have moved that over a little bit more. Okay. Now we are going to plug in. Before I plug in, I'm going to make my life just a little bit, well, either way is fine, I guess. I would probably change this to 1/6 natural log of x minus 4 over x plus 2, just using my little log properties there. But you don't have to. You can just plug in as it is. Okay, if I plug in 1, start at the top, plug in 1, we'll have 1/6. I'm going to factor out that 1/6 too, by the way. Natural log of 1 minus 4 over 1 plus 2, right? Minus natural log of absolute value of negative 4 over 2. And that would be a safe stop spot. That's a safe stop spot. You may have the absolute value of negative 1 is 1, natural log of 1 is 0. So this would be just negative natural log of 2. So that would be another form of this answer, okay? A more simplified form. But definitely try not to go on. Try to safe stop when you can. Anything you can stick into a regular old scientific calculator. Okay, part C. For k is equal to 1, find the value of this integral or show that it diverges. So my first, when I just see the problem, when it talks about diverging, it makes me think, oh, I need to be careful here because there might be some value in this interval that makes something funny happen with my function, particularly a vertical asymptote. So let's write this down and let's see what's going on with it. So I'm putting in 1 for k up here in my function. So 1 over x squared minus 2x plus 1 dx. Okay? And again, because they tell me this, I'm thinking, okay, something funny might be happening here. And when we factor the bottom does factor, right? It factors into x minus 1, which is x minus 1 squared, right? And sure enough, we have got a vertical asymptote at x equals 1, which is in this interval. So the instructions made me question this, made me open my eyes to a possibility of something funny happening, okay? So that tells me I have to break this up into 2 pieces. I need to break it up from 0 to 1 and from 1 to 2. Okay? And now the actual integrals here are not that hard. I can rewrite this, should have wrote this like this just now, but I can at least think of it as x minus 1 to the negative 2, both of these. And then a little in your head u sub, if u is x minus 1, du is just 1, right? dx. If u is x minus 1, then du is 1 dx, right? So this is just a very simple little u sub. I'm not even going to do the u. So I'm going to treat x minus 1 like a u. So the integral will be u to the, add 1 to your exponent, right? And then divide by negative 1, like that. From 0 to, I would like to put a 1 up here, but I cannot put a 1 up there because my function is not defined there. So I cannot put a 1 there. I'm going to put a b there, and do the limit as b goes to 1, specifically from 1's left because it's coming from 0, right? Plus, I'm going to leave a space because I'm going to have to do another limit. Same thing, negative x minus 1 to the negative 1 from, this time the 1 is down here, right? The 2 is fine. Oh, and I'm going to put a little a right there for my lower limit and say limit as a goes to 1 from its right because it's on the side of 2, right? Okay, so this is equal to the limit as b goes to 1 from the left. I'm going to rewrite this as negative 1 over x minus 1. It'll help me. Help me think of this correctly. Okay. Now, we're going to put b in for x, and then let b go to 1 from the left. But, okay, so b goes in for x, and then 1 from the left is like 0.999. 0.999 minus 1, this is, the bottom is going to 0, but it's still negative. The bottom is going to 0, but it's still negative. So this whole thing here is going to negative infinity, but then we have this negative here, so it makes this whole thing go to positive infinity. It's going to positive infinity, right? So this is going to, it's going to infinity minus, if we put 0 in for x, that's not a problem, that's just 1. And you know what? Since we got this for this limit, that means this limit does not exist. I don't even need to go and do that limit because this limit does not exist. Limit as b goes to 1 from the left of this does not exist. Therefore, the integral diverges. If we had done this one too, we would have gotten another infinity. And you'd have like, you would be thinking of it as like an infinity plus infinity. So obviously that diverges. So if you said that, that would be fine as well, okay? This was worth 3 points. I didn't tell you how much part B was worth. Well, let me go do this first. This was worth 3 points. 1 point for the improper integral. Okay. 1 point for the antiderivative. And 1 point for your answer with reason. So improper integral, that means your improper integral, you had to split it up into 2 pieces. 1 point for your antiderivative. So if you got the antiderivative, you would get that point even if you didn't split up your improper integral. And then 1 point for your answer with your reason. Up here in part B, it was also worth 3 points. 1 point for the partial fraction decomposition. One point for the antiderivatives. That's these 2 things here. And then 1 point for your answer. My students didn't like this problem. They had a tough time with it. It was number 5. It's deep into the exam. But I don't think my students quite got to this global. Well, I will say that over my class's average was not quite up to that global average. I did have lots of kids get over the global average, but I had more get below it. Okay, alrighty. So that is the topic on the miscellaneous or the combination problems.